This is the story of the one. As a custodial supervisor at a high school, he knows that during cold and flu season, germs spread fast. It's why he partners with Grainger to stay fully stocked on the products and supplies he needs, from tissues to disinfectants to floor scrubbers. All so that he can help students, staff, and teachers stay healthy and focused. Call 1-800-GRAINGER, click Grainger.com, or just stop by. Grainger, for the ones who get it done.
Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Okay, let's unpack this. Imagine looking up at the night sky and pointing to a tiny distant speck 40 light years away and asking, could there be liquid water there? Could there be an atmosphere? That's exactly the cosmic adventure we're embarking on today. We're diving deep into the mysteries surrounding an Earth-sized exoplanet that's been captivating scientists and stargazers alike. Our star for this deep dive is TRAPPIST-1e, a world that scientists sometimes just call Planet E. Our mission today is to explore the central enigma of this fascinating world, the potential for liquid water, and the absolutely crucial role of an atmosphere in making that possibility a reality. And helping us unravel this cosmic puzzle, of course, is the incredible eye in the sky, NASA's James Webb Space Telescope. For you, this deep dive is a shortcut to understanding cutting-edge astrophysics, revealing surprising facts, and hopefully giving you those aha moments about worlds far, far beyond our own.
And what's really fascinating here is that this isn't just about spotting a distant speck. It's about meticulously piecing together the precise conditions that could support liquid water, that most fundamental ingredient for life as we know it. So yeah, we're going to explore how scientists are using the most powerful telescope ever built to try and detect these faint whispers of an atmosphere. And what those whispers, or maybe their absence, might tell us about this really intriguing world. This journey into TRAPPIST-1 is, it's a prime example of how science actually works. You have initial theories, then groundbreaking observations, and new data constantly refining our understanding. It moves us closer to answers, often in a very collaborative way, and it really challenges us to reconsider what we think we know about potentially habitable environments.
So what exactly is this enigmatic Planet E that has scientists so incredibly excited? Let's start there.
When we talk about exoplanets, often we're dealing with worlds that are just barely detectable, faint blips in the data. But TRAPPIST-1, well, it's an Earth-sized exoplanet orbiting a star 40 light years away. Now, 40 light years sounds enormous, and it is something like 235 trillion miles, but in cosmic terms, that's practically our next-door neighbor. This relative proximity is exactly what makes it such a prime candidate for the kind of detailed observation we're going to talk about.
Right. It's close enough to get a good look, relatively speaking. And it's not just its closeness, is it? The whole system it's in is pretty special.
Absolutely. Planet E isn't alone out there. It's one of 7 Earth-sized planets, all packed quite tightly around a star called TRAPPIST-1. Now, TRAPPIST-1 isn't like our sun at all. It's what we call a red dwarf star, much smaller, much cooler, and dimmer than our familiar yellow dwarf sun. Think about a star that's maybe only about 8% the mass of our sun, barely larger than the planet Jupiter.
Wow, that's...
Yeah, really small for a star. And this means its habitable zone, that Goldilocks region where liquid water could theoretically exist on a planet's surface.
Yeah.
It's much, much closer to the star than Earth's orbit is around our sun.
So Planet EE must be orbiting incredibly close to TRAPPIST-1 to be in that zone. Does that mean it gets baked? Or
that's the interesting part. It is incredibly close. Planet E whips around its star in just 6.1 Earth days. That's its year.
6 days.
6 days. Compare that to our 365. But because TRAPPIST-1 is so much cooler, so much dimmer than our sun, Planet E actually receives a similar amount of stellar energy to Earth. So this puts it squarely within that critical habitable zone. Temperatures are theoretically just right for liquid water, not so hot it boils away, not so cold it's permanently frozen solid. And it's this initial draw, the potential for liquid water, combined with its Earth-like size, that immediately made TRAPPIST-1 a top-tier target for astrobiology research.
Okay, so it ticks the big boxes. Earth-sized, In the habitable zone, that sounds like the perfect recipe. But you keep saying theoretical viability. What's the catch? What's the big uncertainty?
You've nailed it. That's the absolutely critical point and a common misconception when people hear habitable zone. While TRAPPIST-1e really does stand out its size, its position, the presence of liquid water isn't guaranteed at all, not by a long shot. It hinges entirely on one huge, still unanswered question. Does planet actually have an atmosphere?
Ah, right. The
Without an atmosphere, even in that sweet spot orbit, a planet's surface conditions could be completely hostile. You'd get wild temperature swings between the side facing the star and the side facing away. Any surface water could just boil off or freeze or even sublimate, turn straight from ice to gas, and just get lost to space over time. And this brings us right to the big mystery that the astrophysicists at the University of Bristol and a large international team are working so hard to solve. What this really highlights for you, the listener, is that finding a truly habitable world isn't just about location, location, location. It's not just the orbital address. It's about understanding the atmosphere of the planet's climate system, really. Does it have one? What's it made of? How does it act as a thermostat and maybe a shield? That's what dictates if liquid water can actually stick around. It's a delicate balance, and Planet E is this fascinating test case that's really pushing our understanding.
It's truly astonishing that we can even try to detect an atmosphere on a planet 40 light years away. I mean, how on Earth, or rather, how off Earth does a telescope like JWST manage that? Sifting through all that starlight, what's the biggest challenge there?
It is an incredible feat, and you're right, the challenges are immense. Think about it. We're essentially trying to find the tiny chemical signature of a planet's air. A world completely dwarfed by its star from trillions of miles away. This is where NASA's James Webb Space Telescope, the JWST, comes in. It's not just another telescope. It's genuinely changing the game in exoplanet research. It's part of a major international collaboration, too. You can think of it as humanity's most sensitive eye, specifically tuned to see in the infrared, to see what was previously hidden from us.
And it uses a specific instrument for this job, doesn't it? The NIR spec.
Exactly. Scientists are using one of JWST's workhorse instruments, NIR spec, the near-infrared spectrograph. Now, NIR spec isn't just, splitting light like a simple prism. It's incredibly sensitive and specifically designed for the near-infrared part of the spectrum. And that's crucial because that's the wavelength range where molecules we care about, like water vapor, carbon dioxide, methane, leave their most distinct chemical fingerprints.
Oh, okay.
And it's especially vital for looking at planets around cool red dwarf stars like TRAPPIST-1e, because these stars emit most of their light in the infrared. So it means any faint atmospheric signals are, relatively speaking, easier for JWST to read against the star's background infrared light compared to trying to see them in visible light, where a star like our sun shines brightest. It's like having special glasses that filter out everything except the exact chemical signatures you're looking for. Cuts through the noise.
So how do they actually use NIR spec to do this? They can't just point it at the planet and see clouds, can they?
No, not directly like that. It relies on a really clever technique called the transit method. Picture this. From our viewpoint here on Earth, or rather from JWST's viewpoint in space, Planet E occasionally passes directly in front of its host star, TRAPPIST-1e. This is called a transit. As it does, it blocks a tiny, tiny fraction of the star's light, causing a very slight dip in the star's overall brightness. That's actually how we often find these exoplanets in the first place.
Okay, I've heard of that. The dip in starlight.
Right. But here's a really ingenious part for studying atmospheres. Just as the planet starts to cross, or finishes crossing, some of the starlight grazes the edge of the planet. If the planet has an atmosphere, that starlight passes through the upper layers of that atmosphere on its way to us.
Ah, okay. The starlight gets filtered.
Exactly.
Yeah.
Filtered. The chemicals present in that atmosphere, if one exists, will absorb very specific wavelengths, specific colors of that starlight. Every molecule, like water or CO2, has a unique absorption pattern, like a fingerprint or a barcode, in the infrared spectrum. So by carefully analyzing the starlight during these transits, using NIR spec to spread the light into its full spectrum, astronomers can look for these characteristic dips, missing wavelengths within the starlight. Those dips tell them precisely what chemicals are present in the planet's atmosphere. It's incredibly precise work, needs super stable instruments and long observation times.
Wow.
And with each additional transit they observe each time Planet E passes in front of the star and JWST gathers more light, the signal gets stronger. The atmospheric contents, or indeed the lack of them, become clearer and clearer. It's like building up a picture, transit by transit, adding more data points to map out what might be a truly alien sky.
That's absolutely incredible. It really sounds like the JWST-specific infrared capabilities are the game changer here.
They truly are. Dr. Hannah Wakeford, who's an associate professor in astrophysics at the University of Bristol and a key member of this JWST transiting exoplanet team, she was instrumental in designing the actual observational setup for the telescope. That kind of meticulous planning is vital to make sure they get the best possible data for these extremely delicate measurements. As Dr. Wakeford herself put it, JWST's infrared instruments are providing unprecedented detail, helping us understand much more about what determines a planet's atmosphere and surface environment and what they're composed of.
You can really feel the excitement.
Oh, absolutely. She also said, it's incredibly exciting to be peeling back the curtain on these fascinating other worlds, measuring the details of starlight around Earth-sized planets to ascertain what it might be like and if life could be possible.
Right.
And she mentioned it's this careful process of elimination and comparison that's leading to these great new insights, really shifting our understanding of planetary science. It's just a stunning testament to human ingenuity, isn't it?
Yeah.
Our drive to explore lets us ask and now start to answer questions that were pure science fiction just a generation ago. This technological leap with JWST, it just pushes our cosmic reach further than ever before, giving us these tantalizing glimpses into previously inaccessible worlds.
So after all that incredible data collection, all that painstaking analysis, what does it actually mean for Planet E's potential atmosphere? What are the headlines coming out of these first observations, the big reveals?
Well, the initial results are now published actually across 2 separate papers in the Astrophysical Journal Letters.
Yeah.
And they're fascinating, but also, as science often is, quite nuanced and cautiously presented. They're definitely what they call hints of an atmosphere. That's a key phrase.
And it's, okay, not a slam dunk yet.
Not a slam dunk, no. We have to be really precise here. As Dr. Wakeford explained, the possibility that there's simply nothing there, no significant atmosphere at all, can't be completely ruled out just yet based on this initial data. It's very much a careful process of elimination, like cosmic detective work unfolding as we speak, comparing the data to different models. So it's not a definitive yes or no right now, but the picture is getting clearer. And crucially, we're starting to understand what Planet E's atmosphere isn't, which is often just as important in science.
Okay, so what isn't it? What have they managed to definitively rule out with these first JWST looks?
This is actually one of the most definitive findings so far, a real revelation. The researchers are pretty confident that Planet E does not have its original primordial atmosphere.
Its original atmosphere.
Yeah. This is a really crucial piece of the puzzle. It immediately crosses off a major possibility and tells us something fundamental about the planet's history and its environment. To unpack that a bit, we're talking about what's called a primordial hydrogen-based atmosphere. This is basically the initial gas envelope, mostly hydrogen and helium, that a planet gathers from the disk it forms in. Think of it as the leftover gas from the planet's birth cloud. These are thought to be pretty common for young planets, both gas giants and rocky ones like Earth, way back in the early solar system.
So like baby Earth might have had one of these fluffy hydrogen atmospheres?
That's the idea, yes. But for Planet E, the JWST data strongly suggests this isn't the case anymore. It's gone. Dr. David Grant, who is a senior research associate at Bristol and a co-author, explained why. He pointed out that TRAPPIST-1, the parent star, is a very active star with frequent flares.
Ah, the star itself is the culprit.
It seems very likely. These aren't just gentle flickers. They're intense bursts of radiation, powerful stellar winds, high-energy particles blasting out from the star. Over billions of years, this constant barrage, especially when the planet was young, would have acted like a cosmic sandblaster. It would have just stripped off by stellar radiation any light, easily removed gases like hydrogen and helium. So that initial primordial atmosphere, if it ever had one, would likely have been blown away into space relatively early in the planet's history. It's a harsh place to grow up, orbitally speaking.
Right. That makes sense. A very active star would make it hard to hold on to light gases. So if it doesn't have its primordial atmosphere, does that just mean it's a barren rock now? Or is there another possibility?
And this is where it gets really interesting and hopeful. This leads us directly to the concept of a secondary atmosphere. Dr. Wakeford pointed this out specifically. She noted many planets, including Earth, build up a heavier secondary atmosphere after losing their primary atmosphere.
Like Earth did.
Exactly like Earth did. Our early hydrogen-helium atmosphere was lost too. But then, over millions, billions of years, processes like volcanic outgassing released heavier gases from the planet's interior, things like carbon dioxide, water vapor, nitrogen. And then, of course, life eventually reshaped our atmosphere dramatically by adding oxygen. But the point is, planets can generate a new atmosphere from within. So this is the current frontier for Planet E. As Dr. Wakeford put it is possible Planet E was never able to do this and doesn't have a secondary atmosphere, but there's an equal chance one does exist.
So the jury is still out, but the possibility is definitely there.
Precisely. While that initial hydrogen cloak is gone, the chance that it generated a new, heavier atmosphere, maybe rich in CO2, maybe nitrogen, maybe even water vapor, released from its rocks and magma over time, that remains very much an open question. The data doesn't rule it out. It really is like that detective analogy.
Yeah.
Figuring out what's not there, the primordial atmosphere is just as important for narrowing down the possibilities as finding clues about what might be there. And it also really underscores how dynamic these stellar environments are, especially around these active red dwarfs. They can completely reshape a planet's atmospheric destiny. It's not a static picture. It's an ongoing cosmic drama of atmospheric survival.
Okay, so if Planet E does manage to have that secondary atmosphere, that heavier one, what's the next domino to fall in this whole cosmic puzzle? Does that automatically mean liquid water? Because that seems to be the holy grail here.
That's exactly right. The potential for liquid water is the next crucial link in the chain. And yes, if a secondary atmosphere exists, then liquid water could certainly persist on the surface. And if that's the case, researchers are pretty confident it would almost certainly require and be accompanied by a greenhouse effect, something basically similar in principle to what happens here on Earth.
The greenhouse effect, keeping it warm enough.
Exactly. Certain gases in that atmosphere, carbon dioxide is a prime candidate, but maybe methane or water vapor too, would trap some of the heat radiating from the planet's surface, heat that originally came from the star. This trapped heat keeps the planet warmer than it would be otherwise, and critically, it helps stabilize the temperature, preventing all the water from just freezing solid or boiling away instantly. Without a reasonably significant greenhouse effect, even with an atmosphere, the average surface temperature might just be too low for liquid water, or you'd get such extreme temperature swings between the day and night sides the water couldn't remain liquid reliably.
Now, when we hear greenhouse effect, a lot of us immediately picture Venus, right? With that incredibly thick, runaway carbon dioxide atmosphere and surface temperatures hot enough to melt lead. Is that the kind of scenario we might be looking at for Planet E?
That's a really important question, and it's vital we add some nuance there. The lead author on the theoretical interpretation paper, Dr. Anna Glidden from MIT, specifically addressed this. She explained that based on their modeling and the current data, it is unlikely the atmosphere of Planet E is dominated by carbon dioxide, like the thick atmosphere of Venus and the thin atmosphere of Mars.
Okay, so not like Venus, phew, and not like Mars either.
Apparently not dominated by CO2 in the way either of those are, which suggests something potentially different. Dr. Glidden also emphasized, but it's also important to note there are no direct parallels with our solar system. TRAPPIST-1 is a very different star from our sun, and the planetary system around it is also distinct. That's a really key takeaway. We're dealing with an alien solar system, an alien star. We shouldn't expect things to look exactly like Earth, Venus, or Mars. The conditions, the history, the chemistry could all be unique.
Okay, so maybe not Venus-like, maybe not Mars-like. But some CO2 could still be really important, couldn't it, for that warming effect?
Precisely. Even if CO2 isn't the main component, it could still play that crucial greenhouse role. And Dr. Wakeford added a very encouraging detail on this point. She said, a little greenhouse effect can go a long way, and the new measurements do not rule out sufficient carbon dioxide to sustain some liquid water on the surface.
Not ruled out. That sounds significant.
It is significant in scientific terms. It means the observations we have so far are still perfectly consistent with there being enough CO2, or perhaps other greenhouse gases, to keep the surface temperature above freezing, at least in some places. It means the possibility of liquid water, enabled by a modest greenhouse effect, remains firmly on the table based on this initial JWST data. That's a major step forward. Now let's just imagine for a second what that liquid water might actually look like on such a unique world. Because it might not be a global ocean like Earth's. The water could potentially take one of two main forms. Maybe it is a global ocean, covering most of the planet, a true water world. Or, and this is where the unique environment of the system really comes into play, the water might only cover a smaller specific area. Perhaps a region where the star is at perpetual noon, surrounded by ice.
Perpetual noon, surrounded by ice. That sounds incredibly bizarre, like an eyeball staring at the star. I think I've heard that term, eyeball planet.
That's exactly the concept. The eyeball, or sometimes lava lamp, ocean configuration. And it's a direct consequence of something called tidal locking.
Tidal locking? Like our moon.
Precisely like our moon. Because the TRAPPIST-1 planets are relatively large compared to their small star, and because they orbit so incredibly close, the star's gravity has locked their rotation. What this means is that one side of planet E always faces the star, experiencing perpetual daylight, while the other side is permanently turned away, plunged into perpetual darkness and cold.
Wow. A permanent day side and a permanent night side.
Exactly. Unlike Earth, which rotates, distributing heat more evenly, planet E would have this stark contrast. So if liquid water exists, the most likely place for it to pool and persist would be on that permanently warm day side, maybe concentrated near the point directly facing the star, the substellar point. This could form that eyeball ocean, a large patch of liquid water facing the star, potentially surrounded by glaciers or a vast frozen ice sheet covering the twilight zones and the entire dark side.
That paints such a drastically alien picture. Not Earth 2.0, but something entirely different. What would the conditions even be like near that ocean?
Oh, incredibly dramatic, most likely. Imagine constant, perhaps hurricane-force winds blowing from the hottest point under the star towards the colder twilight regions and the night side, driven by that massive temperature difference. These winds would likely drive strong ocean currents within that eyeball sea. You might have intense evaporation under the star, leading to thick clouds, maybe perpetual rain or snow in the transition zones. The Terminator line, that ring of perpetual twilight between the day and night sides, could be a really interesting zone. Maybe temperatures there are more stable, more clement.
It really forces you to think outside the box about what habitable even means, doesn't it?
It absolutely does. How would life adapt? Could something live in the boiling center or the freezing edges, or find a niche in that twilight zone? Maybe life exists under the ice on the dark side, warmed by geothermal heat. The fact that these initial JWST findings are still consistent with enough greenhouse gases to make any surface liquid water possible, even in this strange eyeball configuration, is what keeps scientists so incredibly engaged. It challenges all our Earth-centric biases about what a habitable world must look like. It really broadens our perspective on the sheer variety of potentially life-bearing environments the universe might offer.
This really does feel like just the beginning, doesn't it? This deep dive into TRAPPIST-1e is clearly far from over. These initial findings, these hints, are just paving the way for more. It feels like we found the first few pieces of this incredibly complex and captivating cosmic puzzle, but maybe those pieces just raise even more questions. So what's next? What's on the cosmic research agenda for Planet E?
You're absolutely right. This is very much just the first chapter. The quest to understand Planet E is an ongoing process. The immediate next steps involve, well, more data, more observations. They need to build on these initial forward transit observations. The more times they can watch Planet E pass in front of TRAPPIST-1, the more starlight they collect passing through its potential atmosphere. This will strengthen the signal, or perhaps show its absence more clearly. It will allow scientists to confirm or deny the presence of that secondary atmosphere with much greater confidence, and hopefully start to really pin down its composition. What is it made of? But crucially, it's not just about staring at Planet E. They will also compare its data very closely with data from another planet in the same system, TRAPPIST-1b.
Planet B, the one even closer to the star.
That's the one. Planet B orbits closest to the star, so it gets blasted with even more intense radiation. It's likely lost any atmosphere it might have had even more readily than Planet E. By comparing the atmospheric signals, or lack thereof, from both Planet B and Planet E, scientists can get a much better handle on the processes of atmospheric loss and retention across the whole system. How does this star's activity affect planets at different distances? This kind of comparative exoplanetology, studying multiple planets in the same system, is incredibly powerful. It gives context. It will provide really nuanced insights, not just of Planet E's potential habitability, but about how these common red dwarf stars shape the worlds orbiting them. It's like having multiple experiments running in the same cosmic lab.
That sounds like a truly monumental undertaking. It must involve a huge team. Who are the people behind this kind of groundbreaking research?
It really does highlight the scale and the collaborative nature of modern astrophysics. Dr. Nestor Espinosa, who's an associate astronomer at the Space Telescope Science Institute, the place that operates JWST, and one of the principal investigators focusing on TRAPPIST-1, he emphasized this. He said, Webb's infrared instruments are giving us more detail than we've ever had access to before, and the initial 4 observations we've been able to make of Planet E are showing us what we will have to work with when the rest of the information comes in. That clearly indicates this is a planned long-term campaign. They knew the first look would be suggestive, maybe not definitive, and they're ready to gather the rest of the data needed.
It's part of a bigger program, isn't it?
Yes, exactly. The whole project is part of a larger JWST initiative called the DREAMS program. That stands for TRAPPIST-1e Survey Team. Detailed research for exoplanetary atmospheres and mass loss studies. Quite a mouthful. It's a massive collaborative effort led by Dr. Nicole Lewis, who's an associate professor over at Cornell University. And it's truly international. We're talking more than 30 scientists involved from the UK, the US, and India, including, as you might expect, several current and former members of Dr. Wakeford's team at Bristol. It really showcases that global effort needed to tackle these big questions.
And this team, they have a pretty strong track record already with JWST, don't they? I think I remember hearing about another big discovery they made.
You're absolutely right. This group has already made headlines. They had that breakthrough detection of quartz clouds made of tiny sand-like particles in the atmosphere of a different, very hot exoplanet. That was published back in 2023, a study led by Dr. Grant, the same researcher we mentioned earlier, and co-authored by Dr. Wakeford. So yes, this prior success really underscores the caliber of the team and, again, the incredible transformative power of JWST itself. It shows they know how to use this instrument to tease out really difficult signals. It reinforces that we're not just passively looking anymore, we're actively pushing the boundaries of what we can detect and understand about these alien atmospheres. And, you know, it's always worth remembering the bigger picture of JWST itself. It's the world's premier space science observatory right now. Its mission is broad, distant galaxies, star formation, probing the universe's mysteries. But studying exoplanets is a huge part of that. And it's an international program. NASA, the European Space Agency, the Canadian Space Agency, all working together.
The whole TRAPPIST-1e story is just a fantastic example of this global scientific cooperation, constantly pushing the frontiers of discovery and revealing bit by bit just how much richer and more complex the universe is than we ever imagined. Each new piece of data really does bring us a little closer to understanding our own place within it all.
So we've journeyed 40 light years in our minds today, peered through starlight using the most advanced telescope humanity has ever built, and we found these compelling hints, these tantalizing clues that an Earth-sized exoplanet, TRAPPIST-1e, might just hold on to a secondary atmosphere. And if it does, well, then the potential for liquid water follows. Maybe a global ocean, maybe that strange sun-kissed eyeball pool on a tidally locked world. This isn't just a story about a distant planet, is it? It feels like a testament to human curiosity, to our ingenuity. It really reminds us that we are living in a golden age of cosmic exploration, constantly redefining what's possible to find out there. Science fiction is literally becoming science fact before our eyes.
And what's truly fascinating here, I think, is how these discoveries, even these tentative hints from worlds like TRAPPIST-1, they really compel us to rethink our most basic assumptions about where life could emerge and what forms it might take. If a tidally locked planet orbiting a volatile red dwarf star can potentially sustain liquid water, perhaps in a configuration totally unlike Earth, well, what other completely unexpected possibilities will JWST uncover next? Out there in the vastness. And ultimately, what does that tell us about our own unique, or perhaps not so unique, place in the cosmos? It forces us to broaden that definition of habitable in ways we probably haven't even conceived of yet. It's a profound question to ponder.
Absolutely. A really powerful thought to end on. Thank you so much for sharing your expertise on this deep dive today. And thank you, our listener, for joining us. Keep looking up, keep asking those big questions, and we'll see you on the next cosmic adventure.